Alright, hello everyone. We are back again with another daily Leetcode challenge. This is challenge 1497, or question 1497, and the date for this challenge is October 1st. So we are now into October 1st of 2024. Quick disclaimer, I already have implemented this problem in Java, so we'll be coding this in Java today. Secondly, I'm going to try and do a better job in this video at sort of just diving in, coding it, walking through the solution, instead of rambling on about the various data structures. I will explain the data structures and some of the algorithms, but I'm going to try and do it in a more concise way. So, without further ado, let's go ahead and jump right in. So, the problem today is to check if the array pairs are divisible by k. So given an array of integers, array of even length n and integer k. So in this case, if we go down to the constraints, we can see array.length equals n, and n is even. So we can infer that n, whenever this gets tested, all the test cases go in, n is always going to be even. So we are always going to get an even number of elements in the array we're using. So we don't need to check for that, essentially, and throw any kind of exceptions or errors. So we can just leave that. Essentially, we want to divide the array into exactly n divided by 2 pairs, such that the sum of each pair is divisible by k. So, a little confusing, but look at the examples. And then return true if we can find a way to do so, and return false otherwise, right? Pretty simple. So, with that being said, we're returning true or returning false. So in Java, we're going to be having a method that is of type Boolean, right? Because we're going to return true or false. So, in the first example, the input is an array of 9 numbers, 1 through 9. The k value is 5, and the output is true because there does exist, 1 through 10, sorry, so there's 10 elements in this array, because if it was 9, you wouldn't even be able to do it. So yes, 10. And it gives us 5 pairs that are all divisible by 5. So for example, our k equals 5. 1 plus 9 is 10. 10 is divisible by 5, so we're good. We have 2 and 8. 8 plus 2 is 10. 10 divisible by 5, we're good to go. 3 plus 7, 4 plus 6, so on and so forth. And 5 and 10 are both inherently divisible by 10, so they are also included as a pair even though they're not being added. So that is something that is important to consider that's not really mentioned in the problem description. So we also do need to account for a situation where we do have an element in the array that is already divisible by k. In the case that that happens, we need to find another element in that array that is also divisible by k, because if not, then we can't make a pair, and therefore we have to return false because we cannot do the function that we intend to do. In the second example, similar to see here, right? We have 1, 2, 3, 4, 5, and 6, and we can see we make 3 pairs that can all be added. And right here, in this case, you can see that there's not really any way you can make any of these divisible by 10, right? It's impossible. Right. So, a couple things to think about going into this, and this was kind of the biggest part of this whole problem to wrap your head around is the modulo operator. This actually did take some research for me to figure out too. It wasn't brought on by my own intuition, so I did need to not look up the solution, but definitely get some hints on this one because it is quite an interesting problem. And I believe this problem here has I think it's a 46% acceptance rate for a medium grade problem, so it's quite difficult. It's quite difficult. But we need to think about how the modulo operator works, right? So if we're looking for things that are divisible, right? So that keyword divisible means we're going to be using modulo, right? That's unavoidable. And of course, we all know that modulo will return 0 if the arguments passed to it. Let me step back for a second. So let's say I have 10, right? 10 modulo 5 is going to be 0, right? Because 10 is divisible by 5, right? Because that's inherent in the way modulo works, right? Because it's returning 0 if it's divisible by that number, returning a remainder if it's not. So, for example, 11 modulo 5 is going to equal 1 because we're able to multiply 5 into 11 twice, but we have 1 left over. Similarly, it works the other way if we have a number smaller. So if we say 1 modulo 5, it's just going to return 1. 2 modulo 5, we're going to return 2. So if the number we're using as the first, as the suppose the numerator of the operation, I don't know how to phrase it, but the first number on the left side of the modulo operator, if it's smaller than the one on the right, then it's going to return whatever that number is, the first number is. So what do you think about this for a second? So this equation is key, right? Because we're essentially saying that if we have two numbers, x and y, right? If x modulo k plus y modulo k is divisible by modulo k, or sorry, had returned 0 if we do modulo k, then that means we have a pair. So let's think about this by, let's give an example, right? Let's say we have 1 and 9, right? 1, and let's say our k value is 5, right? So 1 modulo 5 is going to give us 1. 9 modulo 5 is going to give us 4, right? So then we end up with 1 plus 4 modulo 5, which is 5, modulo 5 equals 0. That's correct, right? So it's essentially an algorithm that's going to do the majority of the work here, and it basically function as the backbone of the solution to this entire problem. So we can also rework the problem to be this way, right? As basically a system of equations, right? So if we have x modulo k is 3, for example, then y modulo k has to equal k minus 3, right? If we just plug the value of 3 back into here, we can rewrite the equation to be y modulo k has to be whatever our k value we're looking for is minus the remainder of the first number. So think about it this way, right? Essentially, we are trying to find the equation, the math we're going to use is we're going to find a value, we're going to find the value's remainder, and then we're going to see if we have another value that exists within our exists another value in the array that has a remainder of the divisible number we're looking for minus the remainder of the last number. So essentially it's this. We're trying to find, so we have the remainder of our first number, right? Then we need to find another number that essentially has a remainder of the k value minus the remainder of num1, right? Right. Looking for remainder of num2 has to be the divisible number we're looking for minus the remainder of num1. Right. That's essentially what we're going to be doing. So effectively, the easiest way that I came about to really be able to pull this off, to do this in a relatively clear and concise way was essentially to make a second array to store the remainder frequencies. I know, a little confusing, right? And may take a second to sort of wrap your head around, right? So essentially what that means is we're going to have basically a second array that's going to tell us the frequencies of the remainders we have. A little confusing. I'll show an example. Sorry if I just reiterated what I said 10 seconds earlier. I just had to do a quick cut in the video. But let's say, for example, right, we have an array of 1, 2, 3, 4, 5. Let me just make this bigger. Right? Why don't we? Is there a way to? Whatever. 1, 2, 3, 4, 5, and 6. Right. And let's say the number we're looking to be divisible by is, let's say, 7. Right. Yeah, we'll say 7. I think that I had a previous example where this worked, but yeah, 7. Yeah, that this works. Sorry. So we have k equals 7, right? So then we're going to make a second array of size k. So we're going to make essentially, let's say, like a remainder array of size k. And that's going to exist as the frequencies of the remainders we have. So the remainder array is actually 7, size of 7, right? So our maximum index in this case is 6. So at index 0, we're going to store the frequency of numbers that are directly divisible by k. So in this case, if we had the number 7 in here, this would be 1, because we have a number that is directly divisible by k, but we don't, right? So this is just 0. We don't have any numbers that are directly divisible by k without being added to anything else. Second number is going to be, how many numbers do we have that has a remainder of 1? In this case, we have 1, right? Because 1 modulo 7 is 1, so we have 1. 2, index 2 in this case, we have 2 numbers, or sorry, 1 number that has a remainder of 2, right? We have 2, 1. We have 1 number with a remainder of 3, which is 3. 1 number with a remainder of 4, which is 4. 1 number with a remainder of 5, which is 1, and which is 5, and then 1 number with a remainder of 1, or 6, excuse me, which is obviously 6, so we have 1. So this is just letting us know, and let me see if I can sort of put a little visual aid down here, right? So we have remainder 0, and then we have remainder of 1, remainder of 2, remainder of 3, remainder of 4, remainder of 5, and remainder of 6. So we have 1, that's a remainder of 1, we have 1 remainder of 2, 1 that's a remainder of 3, 1 that's a remainder of 4, 1 that's a remainder of 5, 1 that's a remainder of 6. We're counting, essentially. So this, by doing this, it's going to allow us to essentially count the numbers of remainder solutions we have, and then plug that back into our equation. So now, for example, if any of these end up being like a higher value than the other one, so say this was 2, right? We have 2 occurrences of 2, or 3 occurrences of 2, because that would make this whole thing even, then it wouldn't work, right? We need to have a uniform count across all of our different values, and our divisible by k directly count has to be 0, because if it's 1 or 2 or anything higher than that, then that means we have, or sorry, we have to make sure it's even, rather, because if it's 3 or 4, that means, say it was 3, right? That means we have 3 numbers that are divisible directly by k, which means automatically one of those cannot fit in a pair. So that's instantly going to give us false. So now, with all this in mind, we can go ahead and plug back in to our, well, not plug back in, but start implementing this in this solution. So let's start with our remainders array. Right, okay, we'll call it remainders. Right, we're going to make it an integer array of size k. Now, we need to populate this array with our remainders, which isn't too hard. Essentially, we're going to use our little equation here. We're going to modify it a little bit, and then populate our array with the remainders of the array parameter that we've passed in. So now we're going to need to populate our remainders array. So essentially what we'll need to do is we're going to need to iterate through our parameter array and calculate the remainder of each value, essentially. So we're going to start with a for loop, right? We're going to do a classic for int I equals 0, I is less than the array length, the parameter array, of course, and then we're going to increment I. We need access to the item at index I in the parameter array, but we don't want to modify the actual value in there. We instead want to pull it out and do operations with it, so we're actually going to store the value at I with an integer. We're going to say array at I. This next part is very, very important, specifically because of the edge case where a value within the array parameter, or parameter array, excuse me, is negative. So, for example, when you're doing the modulo operator, or using the modulo operator in Java, there are many cases where it will return a negative value, which is not accurate to how the modulo mathematical operation works. So we're going to need to design an algorithm that is able to return the proper value for doing a modulo operation on a negative value. And here's how we do it. So for starters, what we'll need to do is we're going to take the remainder of our value, of course, at I, and we're going to find the remainder, and we're going to increment the index of that remainder in our remainders array by 1, because we're saying that, okay, we have one case of this remainder at this value, so we're going to increment up, right, as shown in this example down here. So we're going to say remainders, and this is the algorithm. So I'm going to type it out first and explain it. So this is the calculation. So we have the value. Regardless if it's positive or negative, we're going to do modulo k, add k, and then do modulo k again. So this is essentially going to give us a positive value no matter what. Right? It's not going to really affect anything and do anything bad to our operation. So, for example, let's say we had -8 and our k value was 6, right? Yeah, -8 and our k value is trying to think for a moment. -8. Yeah, we'll say -8 and our k value is 6, right? So when we do, if we just did -8 modulo 6 in Java, I believe it would return -2, which is, in this case, not usable because we don't have negative indices in our remainders array. So we can't do that. That's impossible. So we're going to need to convert it to the actual, modulo operation by doing this. So if we did -8 modulo 6, that is, I believe, I believe it's -2. Plus 6 would be 4. 4 modulo. Yeah, in that case it would be 4. Then 4 modulo 6 would be 4. Yeah, that makes sense. Yeah. So yeah, so this algorithm is very important. Definitely keep note of this. Again, I had to do some pretty extensive research on this myself. It took a while because, if you're not experienced with, I shouldn't say experienced, but, Leetcode can throw some pretty advanced algorithms at you. So this requires a lot of thinking to really get down. So yeah, so we have this. This is very important. And this is essentially going to say that if we're going to do our calculation with our value, and we're going to increment and basically add a tally mark to that remainder value. Now what we need to do is check for pairs. So we're going to iterate through our array, our remainders array. We're going to start at 1 because if at index 0, we don't need to make any comparisons because we don't need to check for anything at index 0 because they all have we don't really need to check them, right? Because if our k is 5 and we have values 5 and 10 and 15 and 20, we don't need to compare them together to say, oh, are these two added together going to be divisible by 5? Yes, they are going to be divisible by 5 because in their base form, they're already divisible by 5. So a number that's divisible by 5 plus a number that's divisible by 5 is still going to be divisible by 5, so we don't need to worry about checking that. So instead, we're going to start at 1. And then this is where this little part of the algorithm comes into place. So we're going to say if the remainder index at whatever I is, so in this case at, let's say, remainder 1, right? If we're at 1, remainder 1 is less than the remainder at k minus 1, then we're going to return false. So what does this mean, right? So essentially, we're checking to see that do we have the same number of remainders in this index that we do in its calculated pair, right? Because we said that the second number in the pair is simply k minus the k minus I. Excuse me. It's simply the value we're looking to divide by minus the remainder number, right? So this is this here. So this is saying that if we don't have the same number of remainders as the complementary numbers to that remainder that allow them to add together to be divisible by k, that means that either we don't have the complementary number at all in the array, or we don't have the same number of them, and so we can't make a pair. So let's say, for example, right? I'm trying to think here for a moment. What would be the best? Yeah, if we had, let's say, sorry, I know I keep thinking of examples. Or actually, sorry, this should be not equal to, right? Because if it's less than, there are cases where we'll have more, so that has to be not equal to. But let's say this was, let's see, 7. Yeah. So right, we know the complement to, if we're looking for 7 in this case, right? In this example, if we have remainder 1, we need 6. Right? We need 6 to add to that in order to be divisible by 7. So right here in this case, we're going to check our remainder at 1 is 1. We have one remainder of 1. Then we're going to check to see, do we have one remainder of 6? We don't in this case. So that means we can't make a pair. Or if we had 1 here, then we'd be okay, because we have 1 here, we have 1 here. Perfect, we can make a pair. If we had 2 here, though, that also means we can't do it, because then we have 2 of the complements, and we have 1 here, which means that we'd end up with 1 extra value for the pair, or for the making of the pairs, and at that point, we can't make a pair. So automatically, if we ever find a case where we either can't make a pair or have too many values to make pairs, then we're just going to instantly return false, because we can't do it, right? And then finally, we're going to check one last thing, and this is our final return value. We're going to check to see if our index at 0 is divisible by 2. Reason being, we said initially that index 0 of our remainders array are all the values that are divisible by k. In some cases, there's not going to be any, right? In this case of the example down here, we don't have any numbers that are divisible by 7, so it's just 0. But if this were to be non-even, if it were odd, I don't know why I said non-even, that's ridiculous. If it were an odd number, that means we have a number that's divisible by k, but we don't have one to go with it, so we can't make a pair. So, nope, can't do it. So this would return false in that case. So we're doing one last final check to make sure that we have enough numbers divisible by k automatically to make pairs by checking to see if we have an even number of them, and then it's going to return true if that's true, and return false if that's false, and we're ultimately going to get our answer that way. You theoretically could add a conditional right underneath this. You could put like an if remainders at 0 divisible by 2 is not equal to 0, then return false. But you can just save yourself some code and put it in the return statement instead, which is what I decided to do. So if we go ahead and we run our code, oops, oh, forgot a curly brace. I don't know where that happened. There we go. So, as we can see here, we have passed all of our test cases. And I already have submitted this recently, a couple hours ago. We can see here our runtime beats 98% of solutions, which is quite good. And it actually has, if we analyze the complexity, a big O of n time complexity, which is okay. And it's probably the best we can do. I don't think you can do this in big O of 1. Or log of n. Yeah, I don't believe so. And our memory, which I'm not too concerned about, is O of k. So we did quite good. This is quite a good solution to this. And it runs in 4 milliseconds, which is good. It's actually really, really solid. And funnily enough, actually, it looks like the solution I submitted did use the less than, which shouldn't have happened, but more than likely the test cases that this went through didn't have a case where the number of the first number in the pair to check was not larger than the other. So this should have been on equal to. I did squeeze by, so that did work. But yeah, that's essentially the question for the day. And yeah, if you have any questions about it, just post in some comments and let me know. If there's anything I could have done better, let me know. If there is anything that was unclear, let me know, of course. But yeah, so that's the daily question.